Hello, today we are going to take you through the deep interpretable deep learning for melanoma detection. This is our research problem, and this is Karan's John Mary and Linda Kellen, who are going to be submitting this research. So we came to find out that cancer has been increasing significantly as per reports from World Health Organization, and it is crucial to detect this cancer early so that it is this makes it possible to classify symptoms so that specialists can decide the best arrangement for the patient. So we found out that there are few models that have been developed that enable diagnosis of skin cancer, but many of them don't provide explanations for how they get their results. So this is what we're trying to the gap we're trying to bridge, where we decided to use classical machine learning along with quantum machine learning models with the help of quantum knowledge distillation to improve performance and interpretability of these models. So that maybe if the models are well trained, they are able to be used in practice for this diagnosis. So the problem mainly is difficulty in explaining results from machine learning models. So you find that we have a few machine learning models in this space, but they just give us results. And in most cases, the medical specialists want to know how they came to this diagnosis. So in most cases, they end up not using these models. So then the other thing, need for highly accurate models to reduce misdiagnosis. So you find out that in some cases, uh, due to maybe the test data or whatever the case may be, you find that there are sometimes when models misdiagnose um, different specimens that are provided to them. So we are introducing this quantum neural network so that it enhances on the predictability. So that's why we are saying there is need of highly accurate and transparent skin cancer diagnosis models. So our proposed solution is a hybrid solution. It contains, as earlier said, a classical machine learning model and a quantum machine learning model, which are leveraging the knowledge distillation. So by knowledge distillation, we mean we have a teacher model which goes ahead to process information. Then after processing this input data, let's say our image data, our metadata, it goes ahead and sends the qubits to not the qubits, the logic bits to all the outputs of our classical model to the quantum model. So the quantum model is going to go ahead and do more analysis on this information, which improves the quality of accuracy and prediction. So here we are saying that under the teacher model we are using ResNet 50. The reason why we're using ResNet 50 because it has proved to be um, exceptional with these image data and extracting features and classifying images. Then we have used multi-layer perceptrons for metadata processing so that we are able to get all those correlations that we may not be able to see between these features like age, sex, location of the lesions, among other things. So after that, we go ahead and combine the outcomes of these two models. We put them together into one model. Then after us amalgamating that information, we go ahead and send it to the student model. So in the student model, that's where we may use the parameterized quantum circuits, or another option will be able to use the quantum convolution neural networks. So after this student model receives the information from our teacher, they go ahead and also do quantum analysis on it, then produce the final result, which is more accurate and which is more efficient. Then the knowledge distillation process, here we're trying to explain how it is done, whereby there is need of training our image data and metadata using ResNet and multi-layer perceptrons. Then it extracts soft labels from the teacher model, which are then passed on to the quantum neural network, which is then trained accordingly using KL divergence loss to match the teacher's output distribution. So after this training, you would realize that the the accuracy of the model compared to, let's say, if we are not using a quantum model, is going to increase highly, as we shall see when we go ahead to implement the project. I'll let my colleague take on from here.
Greetings. I'm called Linda Killen, and I'll continue with the EDA. So with the exploratory data analysis, this is the dataset overview. We got this dataset from ISIC, and the dataset name is ISIC Challenge 2019 Training Metadata. So during that training, they collected that dataset, and it's the one we are going to use. It contains 25,331 skin lesion samples with metadata. And this metadata, like, it contains both melanoma data together with bending data and the intermediate, like that kind of cancer. Like, it contains all kinds of cancers. So we found this data useful and better because we wanted something that we are looking at prescribing. If you feed this model your data, we are looking at it giving you feedback on which kind of cancer the person is having, prescribing like something like that. So the data structure is that it consists of 25 columns, including patient details, lesion characteristics, and diagnostic results, together with the metadata. So this data set contains the metadata, which describes every image together with its information about the age, the age of the patients and all that. Then it also contains the image data itself. So realize that our EDA is both the image information, image data, and together with the text data. So going on to describe the missing values. We found out that lots of values were missing. If you get to see, you realize that where there is no red bar, it means that actually there is no value that is missing. But then where there is a red bar, it means that very many values are missing. So you get to realize that the clinical size long column had lots of data missing, around 25,000 data is missing, together with the diagnosis confirm type and many others, the patient ID, the personal, etc. So the data, a lot of data is missing. So given that a lot of data is missing, that means that we need to work on the overfitting using different algorithms. So when you look at the age distribution of the parents, here we get to realize that parents who are anticipated to be prone to skin cancer are parents within the age of 40. You realize around 40, 50 there. You get to see that around 2,500 patients are actually prone of that skin cancer. And then around 0 and 20, they have to be very few, and the growth is exponential. But then it becomes a bit constant between 60 and 80, and then it starts to drop from around 70 or something. But within 40, 45, 55, that means that those people are prone to, and lots of them are prone to skin cancer. Okay, so the sex distribution, here we get to see that actually the male gender prone to this kind of cancer, to the skin cancer, for which we get to see that the number is beyond 12,000, and yet the females are about 10,000. About 18,000, or they're about 10,000 and above. But then the males supersede the females. So meaning that males are prone to skin cancer than females. Okay. So when we go on to the diagnosis distribution, we got to realize that benign cancer, these are the different kinds of cancers. So this graph shows the types of cancers that have been captured in our data set, and our analysis shows that benign kind of cancer is highly suffered by the patients, or has the highest number of patients, or has the highest number of count when you compare with malignant and indeterminate kind of skin cancer. So we get to see that this one has a count of over 12,000, and then malignant has a count of 4,000. So that means that the number of rows, or the data that benign has, is over 12,000, and yet the data that malignant has is around 4,000. So which means that in our data set is imbalanced, and therefore we are looking at undersampling our data. See that we reduce in order to bring out a balance, we will get the benign samples and then reduce them to around 4,000, so that our data becomes balanced. Yes. So when we look at the image EDA, that was enough for the text EDA. When you look at the image EDA, you get to realize that the images are 9,762, and all of them are JPG. So we were able to extract just a sample of these images, a sample. We were able to extract a sample of these images. So this is what they look like, and this is how they are labeled. Every image has its own ID. Then when you look at the class distribution of the skin cancer, we get to realize that still the benign kind of cancer has the highest number of columns, or the highest number of samples compared to the malignant, and then indeterminate and others do not have any. So which shows that our data set is still imbalanced. Then when we look at the color intensity distribution, we get to realize that anyway, with the color intensity, we are looking at the red, green, and blue. That's our RGB. The RGB palette. So when we look at that palette, we get to realize we are looking at the intensity of each of these colors in an image or in a pixel. So just an overview, you'll get to realize that red is highly, it highly occurs in those different images, like in the pixels of those images. And we get to realize that when the pixels are around 200, around a number of around 200 and what, we get to realize that red has the highest number of count. Then we also realize that green also has the same, like the intensity of green in a pixel or in an image is relatively higher compared to the one of blue. So we realize that our images have few shades of blue, lots of shades of red, and moderate shades of green. So our images are light colored. Yes. Okay. Yeah. So this is it for our presentation. This time we'll be bringing out the rest. Thank you.